Okay, so why don't we get started? So welcome back. We are going to start the first topic for the class, which is going to be distributed systems architectures. Okay. Before I start, I wanted to make a couple of announcements. You should follow Piazza posts because we will be posting information there. One of the things we had posted yesterday was we needed volunteers to take notes, scribe notes for each lecture. Okay, one person per lecture, obviously, and then make it available to the class. We will provide you a template and we'll also provide you what was captured last year, that is. Not much has changed. So we would like you to actually go, and there's a sign up sheet there for the next whatever 22 remaining classes. It would be good if you take the initiative and sign up for one of the lectures. Okay, anyone from any section can sign up, and it would be good to do that because when you take notes, you can actually help the entire class benefit from it. Okay, if nobody signs up, none of you get notes, so you will have to just make do with the lecture. That's the way it is going to be. So, and of course, if you do sign up, I will put a small amount of points in the class participation part of the class. Okay, so you will get some benefit putting in there. Okay, so go ahead and sign up. Okay, if anyone wants to volunteer for today's class, let me know now so I can put your name down for the spreadsheet. Anyone want to take notes? You want to take notes? Okay, come and see me at the end so I can take your note. Okay, name down. All right, good. So we have a scribe for today. That's great. So let's start. So I will do a quick recap. So last time I just did an introduction. Your question, yes. Oh, slides are not uploaded. So I think somebody mentioned that I put them up this morning. I think they may not be readable. I will go and fix that. Okay. I think it will take me some time to fix it because I did upload it. Maybe I did not make the file readable. So it is kind of there, but maybe not readable. I'll do it right after the class. Okay. Sorry about that, but I will do a double check next time to make sure that you can get the slides before the class. So sorry about that. We will make sure it doesn't happen again. Okay? In any case, what I was saying was last time I did a quick introduction to distributed systems. And then today we are going to start with distributed systems architectures. Okay, we will have 3 parts to the class. Part 1 will be architecture styles. Okay, we'll do client server architectures, which is part 2, and part 3 is we'll look at decentralized and peer-to-peer architecture. Okay, there's one more thing I wanted to mention, which was, as I said last time, we have a no device policy in the class. Okay, no laptops or phones to be used. Okay, you can bring paper and pencil. Okay, and if you so wish, I can let you use a digital paper and stylus, okay, but not laptops or anything like that. So if you have any devices, there's somebody there with the device. Just reminder that don't use it in class, but you can take whatever type of note taking mechanism you have with paper or stylus is all fine. All right. Okay, good. So let's continue with the first part, which is architectural styles. So what do we mean here, right? So there are various ways to design a distributed systems or applications, okay? And they will be categorized into one of many architectures that are shown here. Okay? So first of all, what is an architecture mean? Okay? So think of an architecture as a way to take the components of your distributed system or application and think about how they are organized and how they interact with one another. Okay? And we will impose some structure on these components and how they interact and so on. And that structure is going to give us some sort of an architecture. And there are several that are listed here, and we are going to go through them one at a time. Okay? So we'll start with layered, then we'll do object-oriented, there'll be data-centric, event-based, and resource-based or resource-oriented architecture. Okay? So let's start with the layered architecture. Okay? So that's shown in this picture here. So in this case, you can take your distributed application and assume that each component is a layer. Okay? And the layers are stacked. Okay? And the restriction on the layer is each layer okay, or each component can only communicate with the component above it and the one below it. Okay, so layer I can only communicate with layer I plus 1 and layer I minus 1. So if you want to, if that component wants to communicate with other layers, you have to go through your neighbors. You cannot directly make a call on others. So that's a restriction we are going to impose. Okay. Now, if you've taken an undergrad OS class and actually got to the networking topic in that class, this picture should be familiar to you because this looks like a protocol stack. Okay. The TCP/IP protocol stack and so on. Okay. So this layered design is used in other contexts. But we are talking here about a distributed system or a distributed application, and the same architectural principle applies to distributed systems or applications. Okay? In fact, there's a very important class of application that you will actually look at and even implement in your labs, which are called multi-tier web applications, right? That map directly to this type of layering. Okay? So what happens in a multi-tier web application is your web application is comprised of what are components that are called tiers. There's tier 1 and tier 2 and tier 3. Okay? And the restriction is very similar. Okay? Each tier can only communicate with the tier that's immediately adjacent to it on both sides. Okay? And we'll look at multi-tier application in a few slides today, but just to give you a sense of a typical web application, what the tiers might be. So the first tier typically is an HTTP or a web server or a web tier. Okay? The middle tier is the application logic, that's the code for the application. And the backend tier is typically a database or a data tier. Okay? So this is a very standard way of designing web applications. It's called a three-tiered web application. Of course, you can have more than 3 tiers depending on the type of application. Okay? That's one example of how you can design a distributed application using a layered approach. Okay? That's the first type of architecture. Of course, if you have any questions, please ask. Okay? The second architecture is called object-based architecture. Okay? So here, each component is referred to as an object. In this case, it's shown as an object. And we remove the restriction from the layered architecture, which says each component can only talk to 2 other components. Okay? That was the layered design. In this case, we allow any component to talk to any other component. Okay? And what we are going to say is 2 things. First thing is these components, and of course that's true for the layered architecture as well, each component doesn't all need to reside on a single machine. That should be clear, because this is a distributed system. Okay? Either the layers or these objects can reside on multiple machines. Okay? So you are communicating between objects, but you are communicating over a network. Okay? And we'll use something called remote procedure calls, which we'll get to in a couple of classes. That's the mechanism that are RPCs that these components are going to use to interact with the other. Okay? The other thing is each component is going to expose a well-defined interface that other components can use to communicate with it. Okay? It just so happens that this interface has to be accessed over a network. Okay? That's your object-oriented architecture. It's a generalization of using object-oriented programming to write a centralized application. Okay? So you have classes that get instantiated as objects. Objects are methods. Methods are the interface to that class. At least the public methods are. Okay? And then you interact with methods by invoking public methods. Right? Now here we are just assuming that those objects can now reside on more than one machine and more than one process on those machines. Okay? That's how we will generalize that principle that you might already be familiar with to a distributed application. Okay? Is that clear? All right. Okay, so let's now go to yet another architecture, which is called event-based architecture. Okay? So in an event-based architecture, so you essentially have a component called the event bus that's shown in this picture here. Okay, that's the thing in the middle. Okay, so that event bus is the component that's responsible for communication, handling communication across these components. Okay? And each of these components can essentially publish data to the event bus. Okay? And that data or events can then be delivered to other components depending on which component needs to receive the data or event. Okay? So there are 2 things to keep in mind here. Okay? First thing is this type of architecture is often used in a class of applications called publish subscribe or pub sub systems. Okay, so what does it mean to say you have publish subscribe type system? So the way communication is going to take place is by publishing data, okay, and then subscribing to data. Okay, so there will be publishers that produce data and get to how to do this type of design much later on. I'm just introducing high-level architectural styles, right? Okay, so event-based architectures is a common way to implement publish subscribe type applications. Okay, and it goes without saying that all those components again can reside on many machines. The event bus would also span multiple machines, okay, because all of this is a distributed system. Okay, is that clear? Any questions? Yes. Okay, I'm not sure I fully understand your question, but you're asking if the publisher and subscriber have different types of data structure. Okay, so as far as the system is concerned, what the internal data structure is not relevant, but what is important is the type of event or data you publish has to be structured, meaning that you have to understand what the fields are and so on. It could be, for example, a JSON object or an XML file or something like that, that you can actually parse and extract what the data is and understand it. And at the other end, you need to be able to consume that type of data. Now, once you receive some data, how you map it into your internal data structure, that's up to the developer. That's not really going to be relevant in terms of how you communicate. That's relevant how you design the application, but not how you communicate between components. Okay? Yes. Okay, that's a good question, and we will, of course, get to this in a lot more detail. But the question is the implementation of an event bus a queue of some sort? Okay, so there's one way to implement event-based architecture, which is using what are called message queuing system or MQS. Okay, there are lots of open source things like ZeroMQ and RabbitMQ. I don't know if any of you heard of any of these systems that allow you to implement it. And it is indeed the case that events will land up in a queue. Okay, the event bus is going to take each event and try to see who has subscribed to this event and then deliver it to those. Right? So all the incoming events will land up in a queue. There may be other queues that you have designed for delivery to other components and so on. So the queue-based implementation is common for designing events. Okay, somebody else had some question. Yes. Yeah, that's a good question. Question is, can you do one-to-one communication or you have to register? So this is a system where you do not do one-to-one communication, okay, because you are not, when you do one-to-one communication, you send a message and you're addressing it to some recipient, and that recipient gets delivered. That's how you are going to do RPCs. We'll talk about socket communication. All the standard methods are one-to-one, and every message you produce has a recipient, okay, that you address that message to, so you know where it's going. Here, when you produce an event, there is no recipient specified. Okay, you just produce an event of a certain type. It goes to the event bus. The event bus sees who has subscribed to this type of events, and you will deliver it to those subscribers. Okay, now of course you can emulate one-to-one by just having one subscriber for a certain event type, but you are still, it's not technically one-to-one in the sense of you're not going to address a message to a certain recipient. You just produce it and expect the event bus to deliver it. Okay, somebody else had a question. Yes.
Somebody decides
Okay, question is, can the event bus be a single point of failure in the system? If you design this well, then you will actually have multiple components in the system that provide the functionality of the event bus. If there's a single machine that this event bus is running, then of course it's a single point of failure. But that gets us into how to make the event bus reliable. Of course, you don't want it to be a single point of failure, so you'll have to design for that. Okay? But as this point, we haven't gotten there. So just think of it as a single queue that you have built. Okay. Yes.
Can we say that this event bus is not access transparent?
Can you say that the event bus is not access transparent, which means you're hiding the access?
You are not hiding that because it is just anyone who gets subscribed or to the event bus knows how all the messages are accessed. So you can say that this is not access transparent.
So first of all, you're using transparent in the opposite way than what it means. Access transparent means you're hiding that you can access it, not you're making it visible. But be that as it may, the components don't actually get to see what the event bus is doing, right? The components are just sitting there. And if an event bus finds an event that's of interest, it just gets delivered to you. So you don't know what other events were processed by the event bus or anything like that. That's internal to the event bus. So it's not like everybody knows what is flowing through the system. Okay. All right. So that is event based. I have one more architecture that is like event based. So this, as you can imagine, pub sub is somewhat different from all these other ones that will map nicely to client server architectures. And there's another one here called the shared data space. That's also somewhat different. Okay. It has some aspects of publish subscribe, but it is actually quite different in the way it works. So here this is also called bulletin board architecture, shared data space. So what is a shared data space? Think of it as a loose collection of data that looks like a database. Okay. So in this case, components are going to go and publish data just as in publish subscribe, but that data can sit in the data space for an arbitrary amount of time. Okay. In the publish subscribe or the event bus architecture, events come in, you look for subscriptions, you deliver them. If there are no subscribers, you say done and drop the data. It doesn't sit there forever necessarily. Okay. In this case, this is like a bulletin board. Okay. You can just go in a physical bulletin board, you can just go and post a note on that bulletin board and sit there for some amount of time. Okay. That note is not addressed to anyone in particular. Maybe it's a note saying you're selling your furniture because you're moving. Okay. And you say, if you are interested, contact me at this number or something like that. So you didn't address it to anyone specific. You just put it there, okay, and hope that somebody's interested in it. And someone can come at a later time, look at that note, and then think whether they're interested or not, and then contact you. That's how a physical bulletin board works. This is the digital analog of it. Okay? In that components can post notices, okay, and they will sit there for some amount of time. Some other components can come and look for nodes or data that match certain attributes. Just as in a database, you can say, is there a node that has this characteristic? Okay? And if there is a match, the bulletin board will deliver that to you. Just as you can go and scan a bulletin board, saying, is there anybody selling a furniture or something like that? Okay? So that's what is called a shared data space architecture. This one is decoupled in both space and time, which means you're not addressing messages to anyone in particular, just as in the previous case, but also you don't expect that your message will be delivered to anyone immediately once you produce it, okay, which you could do assume in the event bus architecture. But in this case, messages might sit forever and might never get delivered if no one is interested in that type. So yes, question.
What does persistent mean in this context?
Yeah, what does persistent mean in this context? Persistent simply means that when you post, the data is going to persist in the data space, which is your bulletin board, for an arbitrary amount of time. Okay? Which technically means you also have to put them on disk. So if you keep it in memory and you restart the machine, then anything that was in the memory is gone. So since it's a persistent, it's like an actual database, right? So you put the data on disk and then it will stay there forever. So that's how you're going to persist your data. Right. So again, we'll get to this later on in the course as to how do you design applications using bulletin board architectures. But let's get to another one that actually is quite relevant to some of what you will be doing in the labs, which is a resource-oriented architecture, okay, or ROA. Okay. There's another name for this that's actually popular, which is called a RESTful architecture. And REST essentially is an acronym that stands for representational state transfer. Okay. Don't worry about why it's called that. Okay. But this is essentially the way you are going to build many web applications. Okay. So what RESTful web services say, or what RESTful architecture says, is that all of the resources that the application provides, okay, can be accessed through a single naming scheme. Okay, that's a uniform naming scheme. So every resource, whether it's a data type, whether it's a file, whether it's some other resource, you will access with the name. Okay, and there's an API that allows you to access it, and that's essentially a unified API. Okay, and moreover, not only can you access that resource with the name, you are going to access it over HTTP, just as you can access web pages through a browser. For this web application, you are going to use a URL. That's your naming scheme. And you can access resources just by constructing the right URL and sending it to the app. Okay? So that's the basic idea, is all of the resources that the application wishes to expose essentially have a naming scheme, which in this case actually is a URL-based naming scheme, and you are going to use HTTP, standard HTTP operation. Okay? So what this means is your distributed application can communicate over HTTP, which is standard for web applications. Okay? Not every distributed application, by the way, has to use HTTP. You can use all kinds of other techniques like sockets or RPC. Okay? But this one actually says that components are going to talk over HTTP. Okay? And the way you're going to talk over HTTP is you're going to use URLs to communicate back and forth. Okay? Any information you need to pass from one component to another has to go as an HTTP request of some sort, and the responses have to come back as HTTP responses. So that's how we are going to design our web application. Okay? And furthermore, we are going to assume that application is stateless and whatnot, which we don't need to worry about, right? Okay, yes, your question. Okay, question is it secure? Is it not HTTPS? You can, of course, use HTTPS, and then communication is going to be secured. But whether it's HTTPS or HTTP, you're still using standard HTTP. HTTPS just encrypts the communication. Okay? You're still using HTTP. It's just that the channel between the two entities that are communicating is encrypted. But then once you encrypt it, you use standard HTTP on top of that encrypted channel. So yes, if you want to secure your communication, you will use HTTPS. But once you do HTTPS, you're still using standard HTTP. Okay? The broader principle is still going to apply. Right? So you can essentially use standard HTTP operations, which are get, put, delete, post. We haven't encountered them yet. We'll get to HTTP later on in this course, and you will see those are standard HTTP requests that you can make, and responses can come back in any form. A typical way to provide a response to any request you make to a component is send a response back as a JSON object, okay? Which is essentially looks like a key value, a set of strings that have a key value type structure in them. Okay, so that's a resource-oriented architecture. Yes, your question. Yeah. Question is, what's the difference between resource-oriented and object-oriented, except for you're using HTTP? Yes, that is exactly the difference. If you write your application as object-oriented, but the objects actually speak HTTP rather than RPC, you're going to get a resource-oriented. Right? So essentially, what resource-oriented architecture says is the way components communicate is using HTTP messages. Okay? And not only should it be HTTP, all of what you are using to communicate has to use a standardized naming scheme that you expose, okay, which is URLs. By and large, you will use URLs, so that you will get for almost free if you are using HTTP. Okay? So that's essentially it. You can take an object-oriented system, and if you use, instead of traditional RPC, HTTP, you will get this type of architecture. Okay? Yes, question there. What does it mean for messages to be fully described? So what that says is, so that was the other thing I wanted to say. First thing is, you are going to, when you have resource-oriented architecture, not keep state at the component. That means that you're not going to keep track of what might have this, what messages were sent by this particular component previously. Okay? So what that means is, every time you make a request, you assume that the other end has no information of what has happened previously. So you want your message to include all the information that is needed for you to process this. Okay? That essentially means that messages are fully described. If you had stateful terms, then you could say, I make a request, I keep some information there. Next time I make a request, I can act on that information. So in this case, we assume no such information is present because you will assume it's stateless. That stateless means you don't keep state. Right? Any other questions here? Okay, so that's a resource-oriented architecture, and perhaps you have heard of yet another one which I did not actually introduce, which is called service-oriented architecture. That's quite common in industry to build applications as service-oriented architecture. I didn't talk about it yet, but I'll quickly describe it on this slide. But what this is showing are three columns: okay, object-oriented, resource-oriented, service-oriented. Okay, so in object-oriented, I'm not going to go through every row, but basically the big idea here is the components of your applications are essentially objects. Okay, objects could reside on multiple machines, and they use remote procedure calls, or if you use Java, you will use something called remote method invocation or a RMI to communicate back and forth. Okay, that's object-oriented architecture. Okay, in resource-oriented architecture, your components. Okay, note that the components don't have to be object-oriented. You can just write whatever code you want, but the restriction is that components are going to talk over HTTP. Okay? Of course, your components could be object-oriented as well, but that's not required. All that we are saying here is communication is going to go over HTTP. You are going to use URLs for communication and so on. Okay? And then you have service-oriented architecture, which was really a precursor to resource-oriented architecture. So the service-oriented architecture, think of it as the previous generation, okay, of what has now evolved to RESTful applications or resource-oriented applications. So they used web-based technologies. Okay, so think of this as a distributed application where the components use web-based technologies, but they don't necessarily use HTTP. There are other web technologies like web services and web service description languages that were designed that looked like HTTP but were not really HTTP. Right? So they said, let's use web technologies for components to communicate, and then you have a service-oriented architecture where each component is a service. It exposes some interface, and you use web technologies to communicate, which is not really necessarily HTTP. There are other types of web technologies like XML that you can use for communication between components. Okay? Now, that just has evolved to a resource-oriented architecture where developers said, if it is a web-based technology, HTTP is the best way to communicate. Let's not try to bring in all other kinds of protocols. Let's standardize on HTTP. You know how to do that. That simplifies things. So resource-oriented architectures have evolved from service-oriented architectures and have simplified and standardized certain things. Okay? So that's the difference between the three. Or some question there, yes.
Why replace cacheable? Not cacheable.
Okay, are objects replies cacheable or not? So in these two cases, because you are sending HTTP or web responses, you can use caching with HTTP. So that's pretty standard because caching is designed to work with HTTP. Okay? But when you have object-oriented architectures, okay, if you're just making Java calls and things like that, typically you're not supposed to cache requests, because if you make another Java method call, you're supposed to actually invoke the object. So it doesn't really work, not designed for it. Okay?
How does caching rely on?
How does the caching rely on the protocol? Caching in this case simply means whenever component makes a request, okay, you can see if the same request was made previously at the other end. If it is made and you cache the response, you just send back the response. You don't re-execute the request. Why can't, so question, why can't it be done? It's just that things like Java are not designed to work with caches. Of course, you can build it, but by definition, you don't put a cache in front of a Java program, right? So you just assume you will re-execute. But in the web, it's natural, so it comes to you as an additional. Yes, question. Okay, what does marshalling parameter values mean? We will get to that in more detail in a class or two. But by and large, what it means is when you are sending a request, okay, you might so think of it as a request is essentially a function call with parameters. Okay, you want to perform some request and you can send some parameters or arguments. Okay, now when you send arguments over a network, you have to send them in a standardized form, because you make no assumption that the other component is running on the same type of operating system or is running on the same type of hardware and so on. Okay, so if you don't standardize it, you might get some data or a network, but you don't know how to interpret it. A simple thing is you might not know whether some data that's come is 32-bit integers or 64-bit integers, because you can't actually assume that the other end is 32-bit if you are 32-bit. So you have to convert all of your data into standardized form and send it over the network. That's called marshalling. Okay? And we'll talk about that when we talk about RPCs. Yes. Is resource oriented a superset of service oriented? It's so we haven't gone to my okay. So service oriented is not the same as microservice, just to be clear. Microservices is actually yet another evolution of web applications. Service oriented is actually an older term than what you might have heard about microservices and so on. Service oriented simply means that you take your application, you partition it into components. Each component is offering a service. Okay? So that's why we call it service oriented. And those services are invoked by using requests that use web technologies as opposed to low-level RPC requests. That's all it means. Okay? Microservices is just a way of writing distributed application. And yes, microservices actually will be RESTful. They typically use resource-oriented architectures, okay? Because this is not really used anymore. Okay? Now, is it a superset? I don't think you can call it a superset or a subset, because there's just an evolution. Okay? So this is saying let's use HTTP. This is saying let's use some other web technologies. They are not directly compatible in that. Yes, but we'll get to microservices soon. All right. So end of first part. Okay, so I already make the announcement about not using devices, so that's fine. We will now switch gears and talk about client-server architectures, which is really a very common way of writing distributed applications. Okay, and we'll now talk about multi-tier and so on. And multi-tier architectures really have evolved into more microservices, but we'll not talk necessarily about microservices today. Okay? But let's first talk about what does client server mean. Okay? So in a client server architecture, as the name client server suggests, the distributed application runs on two types of machines. Some part of your application runs on a type of machine called a server, and the other part runs on something called a client. A server typically is the machine that is providing the service, and the client is the machine that's invoking the service. Okay? And you probably have seen or encountered lots of different types of client-server applications, the most common example being the web. Okay? The web browser typically is the client. The machine that runs your web browser is the client machine. Okay? The web server is the actual server process, and the machine it runs on is the server machine. Okay? And in this case, web browsers are making web requests of the server, and the server is sending responses. Okay? And this is essentially a timing diagram of how the client and the server interact. Okay? X-axis is time. Okay? The dark essentially means that component is executing. Dotted means that component is waiting. Okay? And the way you can think about it is initially the server starts up, it's waiting for requests. That's why it's all dotted. The client starts up, it's executing. It makes a request of the server, and then it waits for the response, which is why you have the dotted line. The request goes over the network to the server executes that request, sends back a response, and the client takes the response, continues execution. And then it might make subsequent requests as well. Okay, pretty standard, but once you understand this, we'll actually have more complicated figures coming down the road. Okay, so that's a timing diagram of how a client and server interact. But what we are really interested in is not that, but how do you design their application as a client-server architecture. In this case, you can also think of it as a web-based architecture. Okay, so here's an example. Okay, toy search engine. Okay, real search engines are not going to look like that. They'll be massively distributed. But let's think of a small search engine. Okay, this one is assuming that you already went and crawled some web pages, you fetch them and you put them into a database and you index them. Okay, that part is done. The crawling is not shown here. So this is your database where you actually went crawled some web pages and you created an index. Okay, now we'll assume that your application, the search engine application, has three parts. Okay, so there's a user interface tier. Okay, that's at the top. Then there's a processing tier and there's a data tier. So there are three big pieces to your application. Okay, typical user interface might just be a search box, okay, or a browser with some sort of input that you want to make. Okay, so that search box, you'll type some keywords and you'll hit submit. Is going to come here to the search engine, to the processing tier, and then those keywords are going to be translated into some sort of a query. Okay, the query is going to be sent off to your database. So now your request comes from the processing tier to the data tier. It's going to come to the database. It's going to retrieve any matching pages that match that query. Okay, so you're going to get a list of responses from the database saying here are web pages that match that query, and you send it to some sort of a ranking algorithm that says let's sort it by relevance. Okay, because I mean many pages, let's see which ones are the most relevant to this keyword. So you're going to order your responses by relevance to the ranking algorithm. Okay, and then you will take that and you will construct an HTML page out of it. Okay, that's your HTML generator. That's the HTML page. And then you send that HTML page back to the user, and they get a web page that shows all the responses. Okay, straightforward process. But what is important from our perspective is to understand the structure of this application. Okay, so you have the user interface tier. That's how the user is interfacing with the system. Okay, that's a user interface. Okay, the middle part, all of those components, the query generator, the ranking algorithm, the HTML generator, that's the processing logic of your application. Okay, that's essentially your processing tier. Okay, or the application, also sometimes called the application tier, because that's the code of the application. Okay, that's the UI of the application, that's the code. And the data tier or the database tier is typically a database that's storing data for them. Okay, it's a pretty standard way to design many kinds of web applications. Okay, so we call this a three-tier architecture that consists of a front-end tier. Okay, that usually has the UI, but also some HTTP processing. And there's application tier that has the application logic, and the data tier that has a database or some storage that has stored. Yes, question. Where would you cache commonly searched queries? That's a good question. This architecture, of course, does not show a cache. Okay, so what you would do if you wanted to have a cache, in this case, you would typically put the cache in front of the database. Okay, so what would happen is every time a query comes and you generate some response, you are going to store the query and the response you generated in that cache. Okay, so now when a new query request comes in, okay, you will construct a query out of that request, and then you will send it to the database. But the database will first look in the cache saying, has this query been received recently? And if you get a cache hit, you will just take the response that was previously generated and send it out. You're not going to make yet another query to the database. So you saved some processing work, okay, because you already cached that previous request. Okay, so you would, in this case, okay, you can put caches at many tiers. But in this case, one place you could put a cache is in front of the database. Okay, but of course you can put it in other places as well. Any other questions? Okay. All right. So I already mentioned multi-tier architecture, client and a server. Okay, three tiers to your application, and then we'll talk about where do you put each of these tiers. Okay, I only showed you these three tiers here. Okay, but I didn't tell you where each of those components are running, because we still have a client machine and a server machine. Okay, so we'll see, depending on where you put these tiers, you'll get different actually systems, different types of systems. Okay, so here's a picture that's going to show you a spectrum of choices. Okay, each of these columns is one way you will design your application. Okay, and there's a dotted line, okay, sort of splitting each of them. Everything above the dotted line says those components run on the client machines. Okay. Everything below the dotted line says that those components stay on the server machine. Okay. And you'll see that we split the application at different places, so you get different choices. Okay. The very first choice is part of the user interface runs on the client because it's above, that's the user interface, and part of it runs on the server. And of course, the entire application code and the database resides on the server. Okay. This is a typical browser-based application. In fact, that search engine example I gave you is exactly going to map to this if you use a browser to connect to your search engine. Because the browser has a simple GUI, which is the search box. Okay. And then at the other end, you might, if you use JavaScript or something, there may be some processing of that user interface at the other end. Everything else is happening on the server. Okay. That's one way you actually partition the three components between the client and the server. Okay. Now let's look at the one in the middle here, okay, which essentially says the user interface and part of the application is on the client. Okay. So, and then there's another part of the application on the server, and the database is on the server. Okay. This is another way you are going to split that three tiers between the client and the server. Okay. Any thoughts on what kind of application might map to this? Yes. Okay, so you can have a richer application in the browser. That will mean some part of it is in the browser, some part of it is in the server. That's one example. There's another example that's actually already on the slide. That's phone-based app. All smartphone apps look like this, right? Your user interface is on the app. There's actually an application you download. So there's some code on your machine, but often your code, that application might connect to something in the cloud. Right? Maybe you have a social media app. So a lot of it is actually running on the server end. Okay? So there's a part of that application is also on the server. There's the part of the app that sits on your phone. The GUI is on the phone databases. So phone-based applications will map to this. They are more heavyweight than browser-based applications. But what you said is also true. You can have richer browser-based apps that look like that as well. Okay? And then you have the last two here, okay, which basically say that the user interface and the application is both on the client end, and then the database is on the server end, or maybe some part of the data is also on the client and some of it is on the server. These are richer applications like desktop apps that you might have, right? So you have a lot of it, processing is actually happening on the machine. Typically, maybe the database is somewhere, or maybe sometimes you might even have part of the data cached locally for performance reasons. So these could be more desktop app kind of scenario. Okay, so you have the spectrum of choices going from lighter weight app parts on the client to more and more things on the client as we get to the other end of the spectrum. Okay, so you can design your application based on what your needs are. This is just showing you that there are all these choices you have as a designer. Okay. All right. Let's continue and go back to our web-based application with three tiers. Now, we will assume in this case that the user interface is at the client, the application and the database tier is at the server. Okay? Just for simplicity, we'll not try to split things. And this is just showing you a timing diagram of how a three-tier application is. Should keep in mind, as you will see, that this is actually an example of the layered architecture I presented. Okay? Each of this tier is really a layer because each tier is only talking to, there are only three. So it's a simple layered architecture. So each one is only talking to the adjacent. So x-axis is time. Okay, so the user interface or the browser is doing some computation. It sends off an HTTP request. It goes to the application server, and then the browser is just waiting. Okay? The application server might do some processing and say, I need to go query a database. So then it sends off a request to the database. Okay? So that's that request. So then the application server is waiting for a response from the database. Okay? So now it's a database that's executing. The other two are just waiting. The database processes the query, sends back a response, that is the query result, back to the application server. It then processes that response, produces an end result, maybe an HTML page for the user. the browser, and then it sends that back. And then your browser is waiting. In this case, we assume it's a browser is waiting all this while. It gets the response, then it computes again. Okay? So that just shows you how requests flow through the system. So the request is propagating from one tier to the next, okay? And responses are flowing backwards. Okay, so if you have tiers 1, 2, and 3, requests flow from the first tier to the last tier. Responses come back, okay, from the last tier back to the first tier. Okay, so that's essentially your layered architecture or a tiered architecture. Okay, when you get to microservices, okay, things get more complicated. These very simple 3 components become many components because your application tier in the microservices is not one piece of code. These are multiple components that interact with one. Okay? So you will not get such a clean request response. You will have your application tier is itself a set of interacting components, each of which is called a microservice. And we'll get to that, but I just wanted to mention that because somebody asked about that a bit earlier. Okay? So, but in a 3-tier architecture, okay, the tiers typically are HTTP processing. If you write that thing in Java, you have a J2EE tier. If you write that in Python or any of the modern languages that you have access to, either written in Python or Ruby or any of these other languages, and the database is any data. It could be a relational database, key value database like MongoDB or something else. Okay. All right. So that is our 3-tier application. Let's now move on. We'll talk about some other types of systems, one of which is called an edge server system. Okay. So first of all, what is an edge server? And then we'll see why is it useful. Okay. So as the name edge indicates to you, what an edge server is it's a server that is designed at the edge of the network, which means it's very close to the end user. Okay. So the network begins where you actually make a connection and you have internet, sort of your internet gateway or your cable modem is where your network is going to start. So that's the edge of the network. So if you deploy servers that are close to users, they are said to be at the edge of the network, as opposed to distant servers that are not close to the user. They are off in the cloud or some far off location. Okay? So an edge server system essentially says you put a set of servers close to users. Okay? Often these edge servers are also called proxy servers. You hear this term proxy. Okay? A proxy is simply an intermediary that sits between a client and an actual server. Okay? So what you have done by introducing a new type of server is you've gone from the standard client server architecture to what is called a client proxy server architecture. Okay? So there are now 2 types of servers. There's the traditional server, okay, that we always had, but there's a proxy server. The proxy server is sitting at the edge of the network and is closer to the user than the actual server, which may be further away. Okay? So you should say, what does this give us? Why do we need 2 servers, and what does it matter where the server is? So think about what can we do if you put a server close to the user. Okay? You can reduce latency because now requests don't have to traverse to a distant server before they're processed. They just go to a nearby server, get processed, and come back. So the user is going to see faster response time. Okay? So by putting servers at the edge or putting proxies at the edge, you essentially improve performance. It's really a performance optimization. Okay? So typically what happens in this kind of architecture is when you make a request, the request is not going to actually necessarily go to the distant server. It will first arrive at the proxy server. Okay? The proxy server can see, can it service the request? Okay? If it can service the request, then it just sends back a response, you're done. Okay? You got a response fairly quickly. As a user, you are happy because you're seeing very good performance when you make web requests or any other kind of. But if the proxy cannot service the request, then it has to somehow rely on the original server to process the request. It could do this by just forwarding that request to the server, then the server processes it and the response comes back, or it can hold the request, make a new request to the server, get whatever that the user had asked, and then send back a response. Either of that is true or is fine, but whatever you do, you will now see a little bit higher latency because you sent a request to the proxy sent another request to the server, and then the response came back. Okay? But the hope is if you put proxies, then many of your requests are going to be serviced nearby at the edge, rather than at a distance. Okay? And a very good use case of this is to put lots of web caches at proxies. Okay? So if you basically have caches that are caching all kinds of web content, and especially these days video content, because this is a good use case for video streaming, where you can put videos very close to the user. Then you make a request for a video or any other type of content. If you get a cache hit, then you are getting the video from a nearby server instead of from a distant machine, which can improve performance for you. Okay? Can also save bandwidth and other things. Okay? And those types of applications are called content distribution or content delivery networks, because they are a network of edge servers that are delivering content. That's a very specific type of an edge server system. You can have edge servers that do any kind of processing. This one is just trying to deliver content from a cache nearby. Okay, all right. So we'll get to edge servers and edge computing a bit later on, but this is yet another architecture to keep in mind. That picture, by the way, is from the book. It's a little complicated, but I do want to explain how it works. So here is essentially the two edge servers. That's the main server there at the top. And the two things at the end, that's our ISP, those are clients. It's not a well-drawn picture, because if you look at this picture, the edge server doesn't look any closer than the real server. Okay? But the way you want to think about this is this edge server is really here at the edge of that network. And this edge server is there so that they are actually close to the client. Okay? So I think the book can do slightly better, but you won't get the basic idea of where the edge server is actually sitting in the network. Okay? Yes? Question? Okay. Okay. Question is the edge server running a subset of the functionality of the main server, or is it running a replica of the main server? Any of those things could be true, because that depends on the application that you are building. You get to decide what runs on the proxy server, what runs on the main server. Is it a full replica? Is it some partial functionality where you say some types of requests can be handled by the proxies, or other types of requests should really be sent to the main server? Okay, that's really an application choice. Both of those could be true. Okay. Anything else? All right. So that's the end of part 2. So we'll now look at a different type of architecture altogether, which are decentralized architectures. They're also referred to as peer-to-peer or P2P architecture. Okay. So first thing is, let's try to understand what does peer-to-peer mean. What's the difference between a client and a server? Okay. So as the name peer-to-peer suggests, okay, what happens in this architecture is you have a set of machines or interacting components, okay, and any component can interact with any other component. There's no distinguished machine called the server anymore. Okay. Any peer can act either as a client or a server, depending on whether it's making requests of other peers or whether it's servicing requests from other peers. So in a peer-to-peer architecture, we remove the distinction of a server. Typically, the server receives requests and sends back responses. Okay? Clients are the ones making requests. Servers are the ones servicing requests. Since you have removed the server from a peer-to-peer architecture, the functionality of the server and the client is both embedded into every peer. Every peer can make requests of other peers, but they can also service requests from other peers. So basically, now you have both of that functionality on every machine. Okay? This is referred to as a peer-to-peer system. Both client and serving server type capability built in. Doesn't mean every peer actually has to service requests, but you can have that capability. Okay? Because we don't have the server anymore. Someone in the system has to service requests. In this case, they are peers themselves. Okay? Now, there are many ways to design peer-to-peer applications, but I'm just going to explain maybe two very simple approaches that kind of give you the high-level idea. Okay. Now, the early peer-to-peer systems were designed for all kinds of file sharing. Okay. You could have some content that you put in the peer-to-peer system. Other peers could search for that content, and then you could download that content. Even today, there are systems that get to BitTorrent in just a moment. They also try to do the same thing. It's used for sharing content across peers. Okay. So now let's say So we are not talking about a specific type of an application, which is simply like sharing files. We're not talking about writing web applications or anything like that. So we are limiting for this discussion a peer-to-peer system that is just sharing files across users. Okay, so you want to look for a certain type of a file or image, you can search for it, and then if there is one, you can then download it from one of the peers. Okay, so now the question is, how do you organize your content in this type of system? Okay, so what is shown in this figure here is a ring. You can see that this is a ring-based topology. So you can think of your peers in the system as having some partial responsibility for maintaining, for managing some of the content. Okay? So let's say there are n files that you want to share in the system. Okay? So you say there are some number of, let's say there are 4 peers. Okay? So then you say each peer has to manage 1/4 of the content. Okay? So we try to distribute the responsibility somewhat evenly. Okay? So then you say you manage this 1/4 of the file, this peer manages another 1/4, that peer manages another 1/4, and so on. Okay? So that's one way you can distribute the responsibility, and that's basically what is shown in this figure, except that you don't know ahead of time when you design the system how many peers there are going to be. It could be arbitrary. So you need to be able to scale up or scale down how much content each peer manages, depending on how many peers there are in that particular system. Okay? So the way we are going to abstract it is we are going to assume that content is just numbered 1, 0 through n. Okay? So what the content is not doesn't matter. Right? You just say every file is numbered and you just number them 0. Okay? Now, whenever you have a peer in the system, it has to pick an ID for itself that also goes from 0 through n. So you pick any ID for yourself that goes from 0 through n. Okay? And then you will be node I, where if you picked ID I, you will be node I in the system. Okay? And then you will have some number of peers that have done the same thing. Of course, no 2 peers can pick the same ID. Right? So what you have is, in this case, a system with 16 files, 0 through 15. They are numbered 0 through 15. Okay? And then the dark circles are actually peers that have chosen that ID. Okay? So this is peer 1, that's peer 4, that's peer 7, it's peer 12, and peer 15. Okay? So those are the peers in the system. There are a total of 15 files, and then there are 5 peers. Okay? So what happens in this case is, by choosing an ID, you are saying that I am going to take responsibility for all files that are numbered from the previous peer to me. So that's how we are going to divide the responsibility. So peers number 7 is going to manage files 5, 6, and 7, because as peer 4 is managing all files that are numbered before it, and so on. Okay? So depending on what ID you pick, you join the network. In this case, the network is a logical ring, as you can see. You will join that ring at that ID, and you automatically get responsibility for managing all of the content from I plus 1, which is the previous peer, to j, which is your ID. Okay? So that's how we are going to manage the content. Okay? So that's division of responsibility. Now, how are you going to search for content? Right? So this is, I don't have the details on this slide, but here is the interesting concept that you have in the peer-to-peer system, which is called a distributed hash table, or a DHT. Okay? What is a distributed hash table? First thing is you need to know what's a hash table. Okay? So hash table is essentially a key value mapping. Right? You specify a key, it's going to give you a value. That's what a hash table does. And it's fast. You can do this mapping quickly. Okay? So a distributed hash table is the same concept, except that the hash table is now partitioned across multiple nodes. Okay? So you can think of a large hash table. Okay? And then you say, you just chop it up into pieces and say, this piece you manage, and this other piece you manage, and so on. Okay? So you have essentially now taken a distributed hash table, and each peer is managing a portion of that hash table. Okay? And the question is, what does this hash table contain? It essentially contains a mapping from the file name to the location. Okay? So because you will say, who has a file, let's say cat.jpg. Okay? So essentially you make a hash table lookup, and you will essentially get a mapping, a value that says it is actually with peer 10. Okay? So this entire organization can be thought of as a hash table, where you are now trying to search for files, and you need to know where the file is located. in the system. That's essentially a key value mapping. The key is the file name, the value is the peer ID. Okay? So you can think of this entire structure as managing a large hash table that's distributed because each node has some portion of it. And essentially, when users come and say, I want to now look for content number 10, okay, somehow you need to be told that that's with node 12, because node 12 is managing it. And that's essentially you're going to be your hash table lookup. Now, there's an interesting algorithmic technique that allows you to do this lookup, which I've glossed over. It's not here, but there's a paper I put on the web page that you can go and read how you are going to do that DHT lookup. Okay, you don't need to know it, but if you're interested in it, you can go figure out. But the basic idea you should understand is essentially this hash table. You're searching for content, you go put in the file name, and what you get back is a node ID saying that's the node that has your content. Okay, so that's how you're going to manage this. Okay, yes. Okay, I haven't gotten to that yet, but I will get to. So question is, what happens if the peer is offline? So one of the things that you have to do when you have a peer-to-peer architecture is you assume that the reliability of a peer is going to be lower than the reliability of a server. Okay? Typically, in a client-server architecture, you can assume that the server is generally up. Okay? Of course, servers can fail, and if it fails, you have to do other things to make sure your system doesn't go down. But it's reasonable to assume that generally servers stay up. Okay? You cannot make that assumption in a peer-to-peer system because peers are normal computers that you use. That could be a laptop. Okay? If you just close your laptop and go somewhere, the laptop is no longer running, so the peer is just going to disappear from it. Okay? So in many peer-to-peer architectures, you assume that there is going to be churn. Churn essentially means peers will come and go. That number of nodes that I showed you is not going to stay at 5. Nodes might disappear, new nodes might join. There's going to be a lot of churn. Okay? And because there is churn, the system has to be designed to automatically remap nodes or files to nodes when nodes come and go. Okay? So for example, if 7 disappears, okay, 7 just goes away, then 12 actually has to take over 7's responsibility because it has to now be responsible for everything from 5 through 12. Okay? So that has to be built into your system. Because otherwise, if a peer disappears, then some content is gone. And some lookups for that content also disappear. So content has to be replicated, and you have to track when peers come and go and repartition the responsibility of who is managing what content as the system actually evolves over time. Okay? This is part of a peer-to-peer system, which typically you don't have to do in your client-server architecture. Okay? Of course, you can have fault tolerance and other things, but this is a lot more common in a decentralized architecture. Okay? All right. So I'm going to talk about another type of a peer-to-peer system, which is called content addressable network. Okay? The main difference, or by the way, I should mention that the ring system that I mentioned here is called CORD. Okay? That's the paper, the name that the paper gave it. It's a structured peer-to-peer system where you have each object has a single ID, one-dimensional lookup, okay, and then it maps to a node. Okay? Now, the next one, which I have on the next slide, is called Content Addressable Network, or CAN, or it's also a DHT. It's a distributed hash table, but think of it as each piece of content has 2 attributes, okay? I and J, or X and Y. What they are is not necessarily important in the abstract case, but in the practical case, you can say it's a file name and a file type. Okay? You can say the file name is foo, file type is JPEG. I'm looking for a JPEG image. Or you can have another file called foo, or it could be a Word document. Okay? There are 2 different types of files. Okay? So you can have 2 types of attributes. So you can say, I want to look for a file called foo, and by the way, it's an image. So then your 2 queries are foo image, and then you do a lookup, and then the distributed hash table will say that's node 10 or what, some node. And so it's still a hash table, but you give 2 inputs. There are 2 keys and 1 value. Okay? So in this case, there are 2 keys. You can generalize this to n dimension. So this is a 2-dimensional distributed hash table. Okay? So for simplicity, instead of numbering all the objects from 0 through n, we are just going to map it to 0 to 1. Okay? Doesn't matter whether 0 to 1 or 0 to n, but you just have 1 dimension is here, and there's another dimension there. So there are 2 dimensions. every piece of content now has two attributes, two keys associated with it. Okay? So they all fall somewhere as points in this two-dimensional space, depending on what content is available. Okay? And the same thing that I said previously is true. When a node, which is a peer, wants to be part of the network, is going to pick a random coordinate x comma y for itself. Okay? Where x and y fall within this. And then let's say that's that black dot. Okay? That's a peer. It chose an ID 0.2 and 0.3. So now it is going to be in the center of a rectangle. Okay? Because you've taken this entire space and you chopped it up. Okay? Each rectangle says all the content with values that fall within that rectangle are your responsibility. That's the same as the ring, which said all the values of content after the previous peer are your responsibility. So now you've taken this and generalize it into 2D. Okay? So essentially, that rectangle is the space of it gives you the region that each peer is responsible for. Okay? So as peer join, you partition this space into smaller and smaller rectangles. So each peer has responsibility for only a subset of the content. Okay? Now that's just a generalization. Now what is interesting is what happens when peers disappear and they join and so on. Okay? So here's an example, okay, where you had peer here which had 0.2, 0.3, another peer joined there. Okay? So then you took this rectangle and you split it into two. And then you said you take charge of this rectangle and then you take charge of all the content in that rectangle. That was easy. If you join an existing rectangle, you just partition it into two and you split the responsibility. But if now a peer leaves, that makes things more interesting. Let's say that 0.6, 0.7, that node here, the rectangle in the middle, that peer just disappeared. Okay? What are you going to do with its responsibility? Okay? You have to give it to some existing peers, but you can't take that rectangle and merge it with another existing rectangle and make it a clean rectangle. Okay? In the 2D, it was easy because if the previous peer left, all of its responsibility became the responsibility of the next peer. Okay, here, it's not as clean. So if this node is gone, then you can do one of many things. You can partition this rectangle into two and then split that node's responsibility across two other peers. Because each peer has to get a rectangle. It can't get an arbitrary shape. So you need a rectangle for efficiency of your distributed hash table. Yeah, hash is actually happening in a rectangular 2D space. Right? So when you leave, things are a little more complicated how to take that responsibility and partition it. But when you join, it's easier. You can join giving existing rectangle, you partition it into two, you're done. Okay? So this is how churn is handled. In this case, it's a little more complicated than the chord system. Okay? But by and large, in terms of expressive power, I don't think that this is any more powerful than the previous one, because you can just take two keys, okay, from CAN, you can concatenate them. Okay, the keys are just strings. You can just concatenate them. You get another key. That could be the key you have in the 1D space. Okay? So if you had foo as the file name and JPEG as the file type, you can just concatenate them. You get foo.jpg and you search that way rather than searching for a file name foo and type JPEG. Okay? So you can do whatever you did in the previous one here, but this just gives you ability to query on multiple dimensions. Okay? Any questions here? Okay, so what I will do is quickly talk about some other peer-to-peer systems and then introduce this notion of a super peer. So the two systems I introduced, which are chord and CAN, are called structured systems because they assign a structure to how content is organized in the system, how nodes join, and so on. Okay? Before structured peer-to-peer systems came along, you had what were called unstructured peer-to-peer systems where nodes could join in an arbitrary way and pick certain number of neighbors, and the network topology could be arbitrary. It didn't have to be a ring. It didn't have to be this two-dimensional space. It could be an arbitrary topology. And then if you have an arbitrary topology, there's no clean way to query a hash table. Okay? You basically have to broadcast every request, and it has to go through all the nodes. You query all the nodes and get responses, which was very inefficient. Okay? So hash tables make the lookups very efficient. In unstructured peer-to-peer system, because there's no structure to the network, The only way to find who has certain content is to ask everyone. Okay? Asking everyone means you do what is called flooding. You flood the network and send this request to every node, get back all responses and see if anybody said yes. Okay? Which is not really efficient at all, but that's essentially how unstructured peer-to-peer systems are designed. And because they were not very efficient, people said, let's design them in a way where you can make lookups very efficient. And that is how the DST idea came along. Of course, I haven't shown you any peer-to-peer system, just telling you what some of the disadvantages were. Okay? But I'll just say that and talk a little bit about another concept, which is called super peers. Okay? So in this case, you have essentially it's a peer-to-peer system. But what we have done in a peer-to-peer system is rather than having the responsibility of lookups go to every node in the system, we will essentially have groups of peers, okay, elect what a leader peer, which we'll call the super peer. Okay. So within each peer will be part of some group, of some small number of peers. Within that group, you will pick one peer and call it the leader peer, which we'll call a super peer. Okay. And you will see in this picture that there are 4 clusters, 4 groups, and the dark nodes are the super peers. Okay. And the white circles are regular peers. Okay. Now, every peer in the system is going to store content like previously. Okay. But only the super peer participate in the lookup. Okay. Because lookup is where a lot of processing goes. Because there are lots of requests and you have to keep asking every node. There's no centralized directory saying who has this file. You have to essentially ask, either doing a deep or through flooding, who has that content. So to reduce that burden, you say we will have the super peers track what content is present within their group, and they will answer for all the peers in them. You don't have to ask the other peers. You just ask the super peer, you know everything that's in their group. Right? So only the super peers communicate for queries, but all the other peers also participate in terms of actually sharing content. Okay? That's the idea. So you assigned a little bit of a hierarchy. In the client server, there's a clear hierarchy between the client and the server. The peer-to-peer said no hierarchy, full decentralization. Okay? And super peer, you add a little bit of hierarchy. It's not quite a server, but it's getting a little more distinguished role than a regular. Okay? So this was designed for scalability. As this peer-to-peer system became very large, okay, to handle the increasing traffic, you added this structure where you said, let's make the system have a hierarchy with additional level called a super peer. Okay. Now, yes, your question. How is a super peer different from what? A network subnet. Okay. So a network subnet is simply a networking abstraction where you can give IP addresses to machines. Okay. And when you essentially try to broadcast packets, you are going to limit it to each group that's called a subnet. Okay. This machines can be on the internet. This is not a local area. Subnets are a local area network abstraction. Okay. So these peers can be anywhere on the network. Okay. All you have done is to say, let's take these 4, put them together in that group. Here's a leader. It's going to essentially answer for messages. So it has really nothing to do with a low-level networking abstraction. This is simply how a distributed application, in this case, it's a peer-to-peer application, is organized. Okay. All right. So you're almost out of time. So all I'm going to say here is this idea originally evolved from an application called Skype, which you probably all at least heard of. Nobody uses it as much anymore. It was quite popular before Zoom and other things came along for audio calls over the internet and so on. So the original Skype architecture was a super peer architecture. The super peers were tracking where users were logged in. So if you want to make a Skype call, right, because everything is just a peer-to-peer, you got to track down where your friend's machine is. Because in this case, the peer-to-peer system is not tracking content. It's simply tracking each user, are they logged in and what is their IP address. So if you want to place a call, you can directly connect to that machine and make that call. Okay? Now, there has to be some way for this entire Skype system to know which users are currently logged in and what are their IP addresses. Okay? That information was tracked as a peer-to-peer system. Okay? So the lookup here is, I want to place a call to this user. Are they logged in? And if so, what are they? What is their IP address. Okay? Now, the super peer architecture was designed for Skype to scale because as there are millions of users, every node or every phone that is connected to Skype starts answering questions about who is logged in, that just creates a lot of extra traffic. So your super peers that track which are the users that are logged in into their cluster, what their IP address is. So the lookups in this case are only handled by super peers. But once you want to make a call, figure out which peer it is, two peers can directly communicate. They don't have to go through a super peer. You can directly make a connection as you do in a regular peer-to-peer system. Okay, so that's how this arrows was a way to scale the traditional peer-to-peer architectures, and then it was used for other purposes as well. Okay, all right. I think we ran out of time, so we will stop here today. There are a couple slides remaining. I'll cover them next time.